Hello everyone and welcome back. Now in the previous video I introduced you to the singular value decomposition, an extremely powerful tool for data science. What I would like to do in this video is introduce you to an application of the singular value decomposition, and in particular put it towards more dynamical systems problems. That is, I'm going to put it towards data from a dynamic problem, something that changes in time, potentially over large swaths of space. Now, the application or the method that we are going to be introduced to today is called Proper Orthogonal Decomposition, POD, P-O-D. Okay? Now, it is really, at its heart, just the singular value decomposition. That's what I'm going to show you. But you might ask yourself, why does it have a new name then? Well, it turns out that the singular value decomposition has been discovered and rediscovered and applied and reapplied over and over and over again by multiple different areas of mathematics. And POD primarily comes from fluid dynamics. Now with fluids, one typically has time-evolving data over large spatial regions, right? This could be velocity fields of a fluid over some spatial region. And in particular, what we would like to capture with POD is these time-evolving macroscopic structures. You know, very, very complicated data, but within it are large-scale coherent structures that evolve with the system. What we would like to be able to do is try to identify some of these and maybe even simplify some of the system, or at least the data we're getting from that system. Now, before we get to an application, let's start thinking about the theory and what motivates this. Now, the typical setting for this type of problem is a function that is of both space and time. I'll just call it f of x and t. X can be multidimensional. It represents space. It could be 2, 3, whatever, 8-dimensional. Time here is just going to be 1-dimensional, though, okay? Now, one thing that if you think back to your mathematics education, one thing you can do with this function is you could introduce a basis expansion. So, for example, what you could do is you could write this function in maybe a countable basis, hopefully a countable basis, as maybe a bunch of time-evolving modes and multiplied against a bunch of spatial functions. Now, if you followed along with my PDE series, you'll recognize this as the basis for separation of variables in partial differential equations, right? In particular, there are a bunch of settings that are well known to us as mathematicians. So for example, if the phi k are sines and cosines, well, then we would call this a Fourier expansion, all right? Similarly, if the phi k's are monomials, x to the power of k, we would call this a Taylor expansion. And if these were Chebyshev or Legendre polynomials, we would call them Chebyshev or Legendre expansions, right? The point is, these things exist and are very well studied throughout mathematics. Not just dynamical systems, not just partial differential equations, but places like harmonic analysis and approximation theory. We are very much interested in these basis functions, and we are very much interested in identifying, in the case of time-evolving data, how these things move through time. Now, one thing that we would really like to do, especially as computational scientists, because infinity does not exist on a computer, we would like to try to approximate these functions using only a finite number of these basis elements. So for example, we would like to identify some capital K that we can truncate up to and hope that we have a good approximation of the infinite series, right? So this is what Taylor's theorem really does. It quantifies this error for us. We have a lot of these error quantifications with Fourier, for example, if we know certain smoothness properties of the function. But here's the problem that has puzzled people for a very long time, primarily in approximation theory or harmonic analysis, depending on which side you're coming from. The problem is that if I fix k, so for k fixed, what basis, right? So what basis, so what I mean by that is what collection of functions phi k best, I'm going to put that in quotation marks, best approximate the function f of x and t. So what is it that I mean by this? I mean that if I say I want to only use a certain number of basis elements, maybe 10 or something that's easy for computation, what's the basis that I should choose to minimize the error between this thing, right? And of course, there's a lot of implicit pieces in that question, right? What do I mean by best? Well, these things should be close. What do I mean by them being close? Well, I have to quantify an error metric, of course, right? And this is a sort of massively ill-defined problem that has been worked on in various aspects after it's sort of properly refined. So for example, some people work on this whenever they start talking about band-limited functions. You'll see people using things like the Slepian basis, right? But there are, for example, analytic functions. People use these monomial expansions. For numerical conditioning. Sometimes you want to use Chebyshev or Legendre polynomials. But this is a very common problem that we have in mathematics, right? Because yes, we can do these expansions. Yes, we can truncate them and get good approximations. But of course, I don't want to truncate this at 100 million terms. That's a terrible thing for my computer. It's going to crash it. So sometimes we like to ask ourselves, what is the best way to approximate these? And this is a very common problem in mathematics, one that I will not answer for you today. But I would like to show you how you can approximate or how you can approach a proxy of this problem using the singular value decomposition. And here's the setting for my problem. I'm not going to assume that I have the original function f of x and t. I'm going to assume that I have a spatial grid. So I'm going to say x1 all the way up to xm. And I'm also going to assume that I have a bunch of time points, t1 all the way up to tn. And so in this case, I'm going to assume that I can create this big matrix, I'll call it F, that is going to be samples of this function at this space-time grid. So for example, the first element here is going to be f of x1, t1. And I'm going to go across in time in the columns, and I'll go space in the rows. Okay, so all I'm doing is taking this big space-time grid, and I'm assuming that I have access to at least approximations of the function that I'm interested in doing this expansion for. So for example, you could think about this as you simulated up a partial differential equation on a space-time grid, and you have access to the approximations of the solution on those grid points, right? That would be given to you as a matrix, just like this. If we take a little bit of accounting here, you can see that this thing, let's imagine it's going to be a real valued matrix. It's got m columns, one for each spatial point, and it's got, m rows and n columns, one for each temporal point. And so here's what we want to do. We want to take the SVD of this thing. And I'll show you why this is interesting. Let's take SVD, so remember it's U sigma V star. And the first thing that we'll do is we'll do a little bit of accounting. Let's take dimensions. This is an m by n matrix. That means that U is an m by m matrix, sigma is an m by n matrix, and V is an n by n matrix. Now, if you look at each column of U, it's an m-dimensional vector. M is the same size as the spatial points. These are what are called the spatial modes. And these spatial modes you can think of as being these phi k functions evaluated at each grid point, right? So k here is representing the columns. Each column is the evaluation of a basis function at each one of your spatial points. Similarly, if you take a look at the size here, each column of the vector v is n-dimensional. That's the same size as time. This is temporal motion. This is how each one of those spatial modes moves in time. It is the ak evaluated at each time point. And the first column of u moves in time according to the first column in v. Second column in u goes with second column of v, so on and so forth. And so you might have the question, what does the singular values represent? Well, the singular values are essentially a weight, right? They're the values that go in front of this basis expansion and tell you which one is most important. In particular, we know the singular values are organized by largest to smallest. So it tells you the first column of u and v is the most important column, right? Second column, second most important. Third column, third most important. And what we can do on top of that is we can look for the reduction of this by looking at the reduced SVD. We could just take the rank R approximation of this thing, if you remember this from the previous video, which means that you're only using the first R modes in the basis expansion. That would be that value of k right there, right? By truncating at the number of modes you're using. And so the first question you can ask yourself is this going to be useful? Well, if you want to compare these things, one way you can do it is you can compare according to what's called the energy formulation. Now, the energy here is coming from the fact that this is used in fluid dynamics. It's a physical phenomenon. It has a physical quantity of energy associated to it. So we're going to use the square of the Frobenius norm of the reduced SVD over the square of the Frobenius norm in the original data matrix F. This thing is a ratio. It's between 0 and 1. As R increases, it goes closer and closer to 1. And you can really think of this as the ratio of information in this sort of compression here, this reduction, versus the original matrix. Okay? So the closer this is to 1, the more faithful this reduction actually is, the less you're kind of losing. Now, this is the basic theory. Remember, it's just the SVD. That is the entire aspect of what's called the POD, the POD, the proper orthogonal decomposition here. Okay, let's take a look at an application of POD. In my case, what I'm going to do is apply this to space-time data coming from the simulation of a spiral wave solution to a reaction-diffusion problem. Okay, so you don't have to focus too much on the specifics of how I'm generating the data. What I want you to notice here is what the solution actually looks like. Here you can see a beautiful spiral pattern. You can see that it's rigidly holding that tight spiral wound shape, and it's just rotating around a prescribed center in space. Okay, now all of this code is available for you to run this on your own. You can generate your own spirals. You can play with the code. You can tinker with it. You can apply it to different applications. You can find all the code to download it on GitHub in the link in the description here. Now, if we just stop this for a moment, what we're going to do is we are going to take data from this spiral wave, and we are going to apply POD to it. So, first thing I'm going to do, because the spiral wave is in a planar domain, I'm going to vectorize the data so that everything is arranged as space and time, just like how we had it with our demonstration that was done earlier in this lecture series. Now you can see that I'm applying the SVD to my matrix F here, which is just the two components of the reaction-diffusion equation. Both of them are just spiral waves in this case. And what I'd like to do is let's take a look at the singular values here. Now, here's what I'm doing. I'm plotting the singular values as a ratio of the total sum of all singular values. So here you can see the square of each singular value divided by the sum of all squares of singular values. Now, take a look at this. Two of them are dominating everything else, right? So you can see that maybe as a ratio, the first two singular values are taking up something like 97, 98% of the information in the matrix. Now, one way that you should think about this, as we thought about in the previous lecture, is that this data is almost two-dimensional. Now, of course, what I fed in is not two-dimensional. If we take a look at this, we have 256 by 256, so 256 squared spatial points. That is enormous. And the points in time, we have 801 points in time. So this is a huge matrix that the SVD is effectively telling us is two-dimensional, almost, right? There's a little bit left over. So here's what we're going to do. We are going to extract these pod modes. Now let's take a look at what comes out of this. So I took these vectorized solutions, and then what I did is I turned them back into two-dimensional sets, so you can see these things as really coherent modes. Now these are the phi k's. On the left is phi 1. On the right is phi 2 in that expansion. These are the first two columns of U. They both look almost exactly the same. They're both big, beautiful spiral shapes. And the third mode, you can see here, still has the faint spiral in the background, but there's not a whole lot there. In particular, what you can see is that if the first two modes are really the sort of spiral shape that we started with, the third mode is kind of filling in the details around the boundaries of the domain, right? It's not really contributing to the actual data of the spiral itself. And then what we can do is we can ask, how do these things evolve in time? Look at the vector components of the matrix V. Now take a look at this. I think this is very interesting. So the first column of V, that's in red, nice sinusoidal oscillation. Second column of V, that's in blue, nice sinusoidal oscillation, just a little bit offset from the red. Now remember, those were these big pretty spirals, and essentially what this is telling us is that those two things just oscillate in and out in time. Now what this tells me is that the motion of that spiral wave going in a circle is really just these two spiral waves blinking in and out of each other, right? So they have this nice steady sinusoidal oscillation pattern. They hold on to this nice spiral shape, and it is the blinking of these two spirals that's giving you the visual effect that they are actually rotating. Now, if you take a look at the motion of the third mode here in green, you can see that it's pretty wild and a little bit unpredictable. And again, that's just because it's kind of filling in the details, right? It's kind of a nothing mode. We saw with the singular values that it's not contributing a whole lot to the sum. Like 97% of the information is held up in the first two modes of this thing. So we could actually try and take a low rank reconstruction. Let's try and do rank 1, 2, and 3 reconstructions here. So let's start with figure 7. So in this case, what we can see is, pardon me, where's figure 7? Here's the true solution, okay? And here is the rank 1 approximation of this thing in figure 8 on the right-hand side. You can see that they look almost identical. There are some small, teeny tiny little noticeable differences here. And that's because the rank 1 reconstruction is only about 50% of the information. But it's pretty darn good if you ask me, right? Without looking too close, they look almost identical. Let's look at figure 9 here. This is the rank 2 reconstruction. Remember, this is about 97% of the information. The energy is about 97% if we use that comparison metric. Here now, details are getting filled in. The spiral tip is in the right spot. You can see, maybe there's a little bit of discrepancy here along the boundaries. But remember, we saw that third mode is what is filling in those boundaries. And so if we look at that rank 3 reconstruction in figure 10, all right, there it is. The boundaries are starting to get filled in. And now we're talking about 99% energy that's being held between these first 3 modes. So in this case, what we're seeing is a massive, massive reduction, right? Think about what's being retained in order to create a rank 1 reconstruction of this. 1 spatial vector, 1 time vector, and just 1 singular value, right? So this is m, the size of space. This is n, the size of time. And this is 1. That is teeny tiny. M plus n plus 1. That is way smaller than m times n that was in the original matrix. Remember, m times n is this huge 65,000 times 801. So that's how many data points were originally kept in the original F matrix. Whereas my rank 1 approximation has only 66,000. Let's take a look at the ratio between these two things, and let's see how much of a cost saving we have here. That's less than 1% of the original information in the rank 1 approximation, right? 1% of the original data to capture about 50% of the information. Similarly, if I did a rank 2 approximation, I would have 2 spatial vectors, I would have 2 temporal vectors, and I would have 2 singular values. And I would take that thing and I would get myself still less than 1% of the original data captured in a rank 2 approximation here that is capturing about 97% of the information of the original problem. And from a dynamical systems point of view, what this tells me is that these spirals, even though they are macroscopic, very complicated shapes, from a data perspective, from a scientific coherent structure perspective, they're not really all that interesting. They're just a couple of 2 modes that flash in and out of each other to give the effect that they're oscillating, right? Something I didn't know beforehand. I thought they just moved in a circle. But what the SVD and the POD tells me is something completely different, and it has completely changed my perspective on spiral waves. So I highly recommend taking your favorite space-time data set and applying these methods. Download the code, throw it at it. It's an SVD computation. It's like 1 line to get this done, and you can find some beautiful information hiding inside of your favorite solutions to differential equations. When we come back in the next lecture, we're going to start talking about dynamic mode decomposition, a related but slightly different version of POD. See you all in the next lecture, everybody.